Hello, everyone. My name is Haipeng Cai, Assistant Professor at Washington State University. I hope you have been staying well and safe. And thanks for joining this session. In this talk, I'm going to present our vision on learning visual semantics, a novel approach to program understanding. Program understanding is a cornerstone in software engineering, providing an important basis for a range of development activities, such as testing, debugging, and adding new features to programs during evolution and diagnosing software security vulnerabilities. Given a program, we got to understand it before we can determine what the problems there might be in the program or make any changes to fix the problems. And this process is typically done and largely done by humans. The question that have long been asked is that can we automate the software engineering process? And part of which is, can we make the machine understand programs automatically? And if program understanding can be automated, we would then potentially be able to let machine automatically deal with as other tasks that are based on program understanding, much as humans relying on manually achieving program understanding to enable manually dealing with those tasks. And that is our vision into the future of automated program understanding, where we let the machine achieve program understanding via visual understanding, which is possible given the technological advances being made in areas like computer vision and natural language processing, especially those empowered by deep learning. Intuitively, images and videos are intellectually easier for humans and computationally cheaper for machines to understand than programs. And this super complex code here on the left-hand side, although not very long, just generates a very simple image about a geometric object. Of course, the image is much easier to understand, even for machines. And we define the visual semantics as the description about program behaviors that can be generated through visual understanding, focusing on understanding the visual outputs of programs. And we refer to as visual software, the software that has visual semantics, that is producing visual outputs that meaningfully demonstrate at least a part of its behaviors. First, we generate program inputs that trigger visual outputs, exercising the visual semantics. Then we extract the visual semantics by understanding each visual output as an image and a sequence of related outputs as a video through deep learning-based visual understanding techniques. And lastly, we describe the visual semantics learned through natural language generation. Next, I'm going to elaborate on each of these three components of visual semantics learning. To extract the visual semantics, we need to first exercise them. And that is generating the visual outputs as the source of learning. We start by identifying the calls to methods that immediately trigger visual outputs. We refer to these methods as visual APIs. And to generate the inputs that exercise a visual API, we will traverse interprocedural control flows from each call set of the API backward to any program entry point. This will result in a set of control flow paths. We then try to solve the path conditions on each of these control flow paths to either identify the path as invisible, for example, the path conditions contradicting each other, or derive input values from solving the conditions using a constraint solver. Then we run the program against these inputs to collect the visual outputs. We learn visual semantics from a given, the given visual outputs through image and video understanding. The figure here illustrates the extraction process through image understanding based on deep learning, with some concrete examples of the new concepts we just introduced, such as visual outputs, visual elements, semantic descriptions, etc. To understand each visual output, this module focuses on recognizing various kinds of visual elements, including objects such as a radio button, and attributes of each object, such as the text label and the color of the object, and spatial relationships among objects, and also the scene type of the image, using convolutional neural networks, which are known to be particularly capable of capturing deep characteristics about visual elements of an image. To train the CNNs, we utilize a symbol of existing relevant datasets to extract GUI elements as visual objects, followed by extracting attributes and relationships among objects using attribute inference techniques. For non-GUI elements, we built the training datasets through a snowballing approach as shown in the figure. We start with example or illustrating programs for graphics and visualizations. With this small number of samples, we run them and create the visual element labels through manual annotation. Next, we use this initial dataset to train an object detector with the capabilities to deduce visual dependencies. Then we use the trained detector to extract the visual elements from additional non-GUI visual outputs and manually calibrate the results so as to augment the training dataset. When the time sequence of related visual outputs is available, we further treat the entire time sequence of visual outputs as a video and extract additional visual semantics from the video through video understanding techniques such as video captioning. And we exploit the temporal structure and attributes of visual objects across the image sequence, in addition to the spatial relationships between visual elements within each image. Specifically, we will compute the temporal information from differencing the semantics descriptions between adjacent visual outputs and add the detected changes in and interactions between the visual elements to the output of the image understanding component. Then we incorporate the resulting labels, the words, to the visual semantic description generation step, which we'll look at next. If there are abrupt changes between the JSON visual outputs, we treat the outputs as individual images and generate the semantic description for each image separately, followed by a text summarization process. Our last module is for generating visual semantics descriptions, which aims to turn the visual content extracted from the visual outputs into a natural language-like representation. We pursue this representation mainly because it is a good way to describe the structural and the semantic relationships among the visual elements in the visual outputs, whereas these relationships are an essential part of functional or particularly visual semantics of software. So generating the human readable and grammatically correct sentences is not relevant here, since the goal is to give this generated description not to humans, but to machines. Specifically, with the list of unstructured words resulting from the image understanding or video understanding step, we generate the target representation using a hybrid approach, combining template-based and statistical approaches as illustrated on the right-hand side of the figure. And we adapt part of the template-based idea by filling sentence templates with the labels as nouns, indicating visual elements and visual dependencies among the elements, as conjunctions, prepositions, etc. To mitigate the tedious and unscalable nature of the template-based approach, we adapt the statistical approaches at the same time. And that is automatically learning sentence templates from a limited training dataset using a state-of-the-art statistical framework. We will use project descriptions and README files from top quality open source project repository, such as those on GitHub, to build the initial training datasets for template learning. For a preliminary foundational approach, we implement part of the envisioned approach using simplified choices for various technical components. For image understanding, we train a CNN model using different types of images of non-GUI objects, such as simple geometric shapes like circles, triangles, etc., and craft the images of standard GUI elements such as buttons or checkbox, etc., and all of these are collected online. For the visual semantics description generation component, we simply adapted a template-based sentence generation method using a simple and manually created templates. We then applied this prototype to 16 programs in 4 different languages and manually exercised them to generate 1 or more visual outputs for each. This prototype achieved 96% precision and perfect recall for the visual semantic description generation step. And the imprecision here was mainly due to the failures in recognizing the visual objects for 2 of our subjects. as a result of insufficient neural network training. Efficiency-wise, generating all these models took only no more than 3 minutes. Beyond this, the time for the prototype to generate the semantic description for each subject was basically negligible. Our preliminary empirical results demonstrated promising prospects of the proposed approach for automated program understanding. Of course, currently we only deal with the visual semantics part, and the functionalities of the software that are not demonstrated in any visual output are certainly not understood through our approach. And those will need complementary solutions. An immediate next step for our work is to realize the full design and evaluate the approach systematically. We will need to train the CNNs with much larger data sets and implement the video understanding step. The extended evaluation will not only assess the precision and recall of the generated visual semantics generation as we currently do, but also the usefulness of these generated descriptions in software engineering tasks that are typically based on program understanding. For example, searching software applications to identify code for reuse. And in sum, we briefly discussed the motivation for automated program understanding to support automated software engineering. We introduced the concept of visual semantics and how to learn them from programs' visual outputs, including exercising, extracting, and describing them. Our early results show promising merits of this envisioned approach. For more details, please check out our vision paper. Thanks a lot for your time and attention watching our presentation.